Howdy, everyone. Happy Monday. Happy middle of the semester. We got the exams graded. Uh, I've asked Dallas to put the answers and the grade distribution onto eCampus. Someone just sent a chat, so maybe the answers aren't there quite yet, but they will be before the end of the day. If you have any questions on the grading for questions 1 through 4, email Connor. For questions 5 through 9, email Dallas. If you're not happy with what they tell you, then go ahead and email me and I will take a look at it. On the whole, the class did pretty well. One student even got the full 110 points, and as you can see, 14 scored more than 100 points, so they're in very good shape for the grades. But even with that, there are quite a few people that are in the A range, and there are a few more than I would have liked at the D and Fs, but hopefully those people will come around. But this grade distribution will also be on eCampus if it isn't already there. Um, Sorry it took 2 or 3 days to get it graded, but this is by far the largest class we've had for 322 by a factor of 2 or so. Any questions regarding that? As of now, our second exam is still going to be as scheduled. Today we should be able to finish molecular bonding, molecular structure, and then we'll get into molecular spectroscopy, and those two topics will be on the second exam. Okay, so our last topic for bonding involves the Hückel method, and basically this is for looking at conjugated organic systems, and the book likes to talk about this, and I like to talk about it because it shows what you can do when you have a whole bunch of orbitals that you want to look at the same time. So in the example molecule that I'm showing you here, all of these carbon atoms, 1 through 6, have a atomic p orbital perpendicular to the ring of the molecule, and all of them then can conjugate and participate in pi bonding. Okay, someone is saying not to apologize for the quick grading. Historically, I've always hoped to have the exams graded by the next class period, but anyway, I'm glad that at least some of you aren't bothered by several days of grading. Okay, so the Hückel method basically says if you have two carbon atoms next to each other with p orbitals that can participate in pi bonding, then they interact by a magnitude beta. Beta, since it's an interaction lowering things to lower energy, it has a negative value. It's minus 65 kilocalories. So here I've said about 65 kilocalories. That's the magnitude, but when we actually do it quantitatively, it will be a negative number. So we put betas wherever atoms touch. So row 1, column 2 means atom 1 touches atom 2. Row 1, column 4 means atom 1 touches atom 4. Row 4, column 3 says atom 4 touches atom 3. All the other interactions are assumed to be 0. In real molecules, zeros are pretty good approximations, but they aren't exact. You might have some small interaction even from 2 to 6, for example. So this is definitely an approximation. And the fact that we're assuming all pi interactions to be the same is not correct. You should be able to see that 3 to 6 will have a slightly different bonding interaction than 1 to 2, for example. But this is the approximation that we're making. Okay, so let's put this into practice, and I'll start with the smallest possible molecule with pi bonding, and we'll take ethylene, which more technically I guess should be called ethene. But we're going to look at the interaction of carbon atom with carbon 2 forming the pi bond. In organic chemistry, you learn this has a sigma bond and a pi bond, and I think all of you have seen what that looks like. So here I'm relating this back to our beginning discussion of molecular bonding when we talked about H2 plus. And so we had integrals that looked like this. And so along the diagonal, we always had things like H11, H22, H33, and so on. And that indicated the energy of the atomic orbital that corresponds to those subscripts. So H11 represents the energy of the p orbital on the carbon atom number 1. And on the previous page, we decided that that was alpha. So along the diagonal, we'll always have alpha minus E that goes into the equation. And then H12 is the interaction between 1 and 2. And since they touch, we decided that was beta. So this is the determinant that has to be solved for ethylene. Now back on this page, I also suggested making the approximation and simplification. It's not an approximation, it's just a simplification. We set alpha equal to 0 and beta equal to 1. And that's going to make our answer come out in beta units, and then relative to 0 being the atomic energy of the carbon atom. So here's our determinant that all of us should be able to solve. Minus C times minus C is plus C squared. And then the product this way, we take a minus sign, so that's minus 1. So it comes out E squared minus 1. Solutions are E plus or minus 1, and they're in beta units. So this is how we depict the molecular orbital interaction. The p orbital on carbon 1, it's a 2p orbital, interacts with 2p orbital 2. It forms the pi bond at beta units below the atomic orbitals. So that'll be about minus 65 kilocalories. Beta is negative. And at the same time, we form an orbital minus beta, or about plus 65 kilocalories higher in energy. So again, I don't know if your organic professor told you about antibonding orbitals, but this pi interaction causes both of these orbitals to be formed. Fortunately for ethylene, we only need to put electrons into the lower orbitals, so our pi bonding energy stabilization will be 2 electrons times beta, or about 2 times 65 equal to 130 kilocalories per mole. If you like kilojoules, multiply by, I think it's 3.8. Okay, well, let me show you a couple other systems. These might not be the most common ones you run into in organic chemistry, but people have made the conjugated C3H3. So each of these carbon atoms has a CH bond and a carbon-carbon bond, but it's left with a p orbital perpendicular to the 3-membered ring. So this is now going to be our determinant, and I'm going to skip the stage with the alphas and betas and simply go to minus E on the diagonal and 1 wherever we'd have a beta. So carbon 1 touches 2, it touches 3, so we put both 1s. 2 touches 1 and 3, 3 touches 1 and 2. So this is our determinant. Now you may or may not have expanded 3 by 3 determinants. I would not expect you to have to do that. But if you care, it's minus C times minus C times minus C. That gives us the minus C cubed. Then it's times 1 times 1 times 1, plus 1 times 1 times 1. And then doing all the multiplications with negative signs this way. So we have a minus times a minus C times 1 times 1. That's going to give us a plus C. And ultimately, this is the result that you get. If you do your high school algebra and then factor it, you'll find that the energy solutions are 2, minus 1, and minus 1. In our cases here, the positive numbers mean positive beta values. And since beta is negative, they're good for bonding. So minus, or the 2 beta comes down here. 0 indicates the dotted line for the atomic p orbital that you would have on each of these carbon atoms. Then we have 2 orbitals at -1, or about 65 kilocalories above the atomic orbital up here. And you'll notice that they're exactly -1, both of them, so these are degenerate orbitals. Okay, so we have 2 electrons, each gaining 2 beta in energy, so that's going to be 2 beta plus 2 beta. 1 electron in an antibonding orbital, decreasing our net pi bonding energy, so the net bonding would be 3 beta. I have a chat question. So how did I get minus e cubed? It's the rule that you may or may not have learned in high school for how to expand a 3x3 determinant. You're not responsible for having to do that in this course, but you can look it up. Yeah, somebody else answered that you have to do a linear algebra problem, and you may have done it in high school. I think in my high school, they didn't teach us how to do that, and they didn't teach us about factorials, but we all caught up in college. Okay, so I just picked these 2 examples because they can be solved exactly. Okay, I'll give you 7 seconds to answer, but how can I make C3H3 more stable? So send me a chat and let's see if somebody can win the booby prize here. 3 seconds to go, no chats, there's one answer. Promote an electron. No, that would make it worse. If you move the electron from a lower orbital to a higher orbital, you'd lose bonding energy and you'd have more in the antibonding. You remove an electron is the answer. So C3H3 plus, with this 1 electron removed, you see would have 4 beta in pi stabilization. And in fact, that ion is a known cation that people have made salts from. So you can make things like C3H3 plus Cl minus, and you can crystallize it. It's very reactive, but I think you can study it for a while. So get used to looking at these diagrams and deciding where you get stabilization from it. Okay, on this same page, I've said butadiene C text, but we'll look at it this morning, a few pages later, so I'm skipping it for now. But now let's set up the benzene problem. And when I've talked about benzene in previous classes, in many cases, the students have only heard of the 1 pi bonding benzene orbital that's the most stable and most famous. It actually turns out that there are going to be 3 bonding pi system orbitals. But first, we have to set up the secular determinant, and to be quite honest, I'd have to go back to my notes to figure out how to expand this one also. You can use mathematical software, which some of you might even have on your graphical calculators or something to solve it. But basically, again, the method to set up the determinant is the same. Atom 1 touches atom 2 and touches atom 6. So we would put 1s in those places, 0s everywhere else where 1 does not touch 3, 4, and 5. 2 touches 1 and 3, 3 touches 2 and 4, and so on. 6 touches 1 and 5. When you solve this determinant, you get these energies here. You can ignore the symmetry symbols for now, but symmetry can be applied to these. You get 1 orbital at 2 beta of stabilization of lower energy than 0, and 0 is defined as the atomic carbon p orbital energy. And then you get a pair of orbitals, so they're degenerate at the same energy, 1 beta below the atomic energy orbital. Then you get 2 orbitals, 1 beta unit above, and 1 orbital, 2 beta units above. So this is what the orbitals come out for benzene. Now, in your notes, we have let me see what you have next. There's some peripheral supplementary material that I'll come back to later, but I'll go ahead about 3 pages and talk more about benzene here. Okay, first of all, we can mathematically solve what the wave functions come out for benzene. So here they're written as phi's. Think of each phi simply as an atomic p orbital. So our lowest orbital is going to be with all the plus sign wave functions from the atomic orbitals lined up. P1 plus P2 plus P3 plus P4 plus P5 plus P6. And so this is perhaps a way that you have not seen that pi orbital drawn, but I think all of you know what it looks like. You have a plus lobe of positive wave function above the benzene ring, and then you have a minus lobe below the ring. So try to understand this depiction of these orbitals that we have. The plus means it's plus, 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 plus. And in organic, you saw nice donut-looking pictures with a donut above the benzene ring and a donut below the benzene ring. And the two rings had opposite signs, SIGN, of the wave function. So if someone has trouble understanding what this is, please send me a chat. But I don't have a way to draw that other picture for you right now. So hopefully everybody understands it. I've drawn, or I'm showing the same basic energy diagram for benzene that I had on the previous page. The book that I took this out of took this doubly degenerate pair of orbitals and split them apart just to show you there are two orbitals. And the circles here indicate electrons. They don't indicate orbitals. In my picture up here, I had electrons in each of these orbitals. I mentioned this last time, but note when you were having conjugated systems like this, be it C3H3 or benzene, each carbon atom donates or contributes 1 electron to the system. So we got 3 electrons from here. We got 2 for the ethylene pi bond. And in benzene, we get 6 electrons, and they go into these orbitals as shown here. Okay, so these 6 electrons are supposed to look the same as they did in the other diagram. 2 beta below, 1 beta below, and then no electrons in these anti-bonding orbitals. Later in the course, when we talk about electronic structure, we could talk about an electron jumping from this orbital up to there. It would cost it 2 beta units of energy to move up there, and it would wind up absorbing light in the ultraviolet region. Benzene is colorless, means that any absorptions are higher in frequency than in the visible range. Okay, but now to these orbitals, which you may not have seen in organic chemistry. Here is the depiction of one of these orbitals, 2Phi1 plus Phi2, and it's got a plus Phi6. And then the other ones are minus. So the 2Phi1 is here, the Phi2 is there, the Phi6 is there, all with the plus signs. So between these atoms here, let's label them 1, 2, 3, 4, 5, 6. Carbon atoms 1 and 2 have a bonding interaction. Carbon atoms 1 and 6 have a bonding interaction. And down here, carbon atom 4 bonds to 3 and 5. So those are interactions. So we have 4 bonding interactions. But between 2 and 3 and between 5 and 6, we have anti-bonding interactions. Plus to plus is good. It creates bonding. Minus wave function to minus atomic wave function is good. But plus to minus is bad. So if you count up the interactions here, we have 4 bonding interactions, 2 anti-bonding interactions. And so we know that the net pi bonding from this orbital is not going to be as much as this lower one, which had 6 interactions, 1, 2, 3, 4, 5, 6, all the way around the ring. So the net result is then these orbitals wind up less stabilizing than this lower orbit. Okay, but notice electrons in the lowest orbital each will contribute 2 beta to stabilization. So we get 4 beta stabilization from here. Each of these 4 electrons will contribute 1 beta of stabilization, or a total of 4 beta units. So the net pi bonding stabilization from these 6 electrons is 8 beta. And if the organic professor just talked to you about this lowest one, he or she only talked to you about half the stabilization that you actually get for benzene. So be sure by the time we get to the next exam, you're able to know where to put in electrons in the bonding and anti-bonding electrons, be able to calculate the net stabilization. And in cases like C3H3, note that you can get a more stable molecule by taking off an electron, or in some cases, adding an electron. Question I have is, you said minus to minus is bad. Yes, that means minus to plus plus to plus and minus to minus is good. By bad and good, I mean whether it stabilizes or not. And as I keep telling you over and over again, everything in nature wants to go to its lowest energy. So we want to get these electrons to as low a possible energy as we can when we do this. Okay, so these are the mathematical representations of each of these orbitals. Let me just look at what's labeled B here. And you notice it's +1, -2, +3, -4, +5, -6. So each alternating p orbital flips upside down. 1 is up, 2 is down, 3 is up, 4 is down, 5 is up. If you can read these signs, 6 is down. And so this would be our most anti-bonding orbital that we have. And so that's this orbital shown right here. So one thing I like to do on the second exam also is sometimes give you pictures of orbitals and ask you to order them in terms of energy. We didn't mention these 2 orbitals. They each have 1 bonding interaction, this one between 2 and 3 and between 5 and 6. But then the other interactions are bad, minus to plus. So if nothing else, what I hope I'm demonstrating for you is the importance of knowing the sign of the wave functions when you make atomic orbital combinations. You want to mesh up plus to plus and minus to minus. In my other course, we talk about symmetry, and the symmetry rules help you decide exactly how they're going. These orbitals here, these are what are labeled E2 on the diagram there. And you can see they're not quite as destabilizing as the orbitals up there. Okay, so benzene is a very important molecule, obviously, and there are many, many aromatic systems that chemists, chemical engineers, and other people are concerned with because they're everywhere in coal and oils and everything. Okay, let's also talk about butadiene. This is the way I've drawn it, is transbutadiene. I've left off the hydrogens, but you probably saw this in organic chemistry, drawn like this with a single bond in between. But you were probably told that you had conjugation because you had a p orbital up here and p orbital up there. And so you'd have pi bonding character in the middle also. Incidentally, I might tell you that for years and years and years, people have known there's a second structure, second conformation of butadiene, and everybody used to assume it was a cis structure where carbon 4 would be down in the bottom. But something like 6 or 7 years ago in my own laboratory, I had a very good graduate student taking spectra of the molecule, And we could prove that about, if I remember correctly, 2 or 3% of the natural abundance of butadiene is actually a gauche form. It's not all the way to cis, but carbon atoms 1 and 4 are kind of at angles to each other. So cis is not the second form of butadiene that actually exists. But let's look at transbutadiene. All of you should now be able to write this determinant. Carbon atom 1 touches only 2, so we put a beta there. It doesn't touch 3 or 4, we put zeros. Carbon 2 touches 1 and 3. 3 touches 2 and 4, and 4 touches only 3. So this is the one that has to be solved. I took the answer and picture here out of a book. Maybe even your book has this same thing. But they say we use mathematical software and diagonalize this matrix. And you'd understand that if you'd had a linear algebra course. And this is the result that you get. And so you actually get the energies along the diagonal as a result, and all the other elements in this result wind up being 0. When you do this, the mathematical process also tells you what the wave functions are. So in column 1 here, this is psi 1, and it tells you how many times you take P1, P2, P3, and P4. So the lowest energy wave function, that's the one here, it's plus 0.372 of P1, 0.6 P2, 0.6 P3, and plus 0.3 of P4. And so the representation of this lowest energy orbital looks like this. White here, white color or light color indicates a plus sign, and you can see we're going to plus to plus to plus to plus. But the circles sizes also indicate how large the coefficient is. So the middle orbitals have greater contributions than the outer orbitals for this case right here. Okay, I have another chat question. Someone asks, alpha minus E denotes a double bond? No. Alpha minus E is the mathematical form that we write. So let's go back to here. So these are the rules for setting up the Hückel secular determinant, as it's called. The on-diagonal elements involve an H11 type term, which represents the energy of the atomic orbital, and you wind up with minus E along the diagonal. So go back to your initial notes on molecular structure when we talked about H2+. When we apply the variational theorem and try to solve for energy levels, we get a bunch of simultaneous equations, and then the determinants come from those simultaneous equations. What I'm trying to show you in these is just the shorthand, quickie, simplified way of how you set up the determinants, and from where we get the answers that I'm wanting to show you right now. Okay, so this is our secular determinant, and then the energy levels are given along the diagonal terms here. They're shown right here. So here we've included the alpha. So C2p means that's alpha energy, or the energy of the carbon 2p orbital. When we write alpha plus 1.62 beta, remember beta is negative, that means we're going to be something like 100 kilocalories in energy lower than the atomic orbital. So this is our lowest orbital. Again, I emphasize it's plus to plus to plus to plus. And if I drew you a picture of this orbital, you should immediately be waving your hand and say, hey, professor, this is obviously the lowest energy bonding orbital. To jump to the other extreme, here is the alpha minus 1.62 beta. It's the highest energy. And notice it goes plus to minus, plus to minus. Dark circles here represent minus wave functions. And again, the sizes of the orbitals indicate that they can have different contributions from each of the orbitals. So if you look at the molecule, you can see carbon atoms 1 and 4 are equivalent. And so in any of these drawings of the overall molecular orbital, you expect them to be the same size. 2 and 3 have the same orbitals, alike orbitals, but they're different from 1 and 4. So if you look at this picture here, my little circle here should be the same size as the one on the left. 1 and 4 are equivalent sized, 2 and 3 are the same size, but they're not the same because they can contribute differently. So the coefficients are in the table here. You can see 0.3 and 0.6. More chat questions? Is there a reason why the highest energy goes from P4 to P1? We could have labeled them anyway, so we just want to identify them the way they are. P1 through P4 are actually all exactly the same energy. I think maybe the question meant why are the different wave functions, psi1 through psi4, labeled in a particular way. So it's pretty much up to you how you do it. When you apply symmetry, you have symmetry rules. You start labeling the highest symmetry orbital as psi1, then the next lowest energy of that same symmetry, psi2, and so on. So there are conventions there. Then the next question is, would all negative orbitals have the same energy as all positive orbitals? The magnitude is exactly the same. So you notice this is minus 0.62 above C2P, and this is plus 0.62 below C2P. So this is just as much up as this one is down. The lowest energy orbital is just as much down as that one is up. So if you think about it, if I added up the energy of all 4 of these molecular orbitals, it would be essentially exactly what 4 carbon p orbitals would add up to. So I hedge a little bit because if we get into nuances, then maybe it comes out to be just a little bit different. But in the models that we're using, the Huckel method, the total of all these orbital energies comes out to be alpha in this case for the energy of the atomic orbital. Okay, I don't see more chats, so I'm going to go back. Actually, I'm not. I'm going to go forward in my notes, but it's back in your notes. Okay, so if you go back a couple pages, I've got this here, and in your notes, I didn't label it as supplementary detail, but you might want to write that in. So this is sort of the nuts and bolts of what we just did, written in mathematical form. So some years ago, when I taught a course on symmetry and molecular orbitals, this was typed up. This is way before we even had word processors. But it's kind of a summary of the detail of what we just did. So we're doing the molecular orbital method, MO. It's linear combination of atomic orbitals. Mathematically, it means we take some atomic orbitals, phi sub I, and we sum them. So phi1 plus phi2 plus phi3, etc. You remember we did exactly that for the benzene lowest orbital. And we have different coefficients in front of them, so we can take them by different amounts. And the summation says that this is summation over I, and so it's arbitrary how many atomic orbitals we're going to start from. In the example I'm going to show you, we're going to start from 10 atomic orbitals and see what kind of results we get. In the case of butadiene, we started with 4. In the case of benzene, we started with 6. Okay, the next part, this is what we did when we talked about H2+, so I'm not going to spend any more time on it. We set up these integrals, which came from the variation theorem. These were the simultaneous equations we got. In the case of H2 plus, we only had the first two equations. But when we have n of these expressions, and n in our example is going to be 10, then you would have 10 simultaneous equations, and you can set up a determinant that's 10 by 10. Your mathematical software can solve it for you, and you get the answers. Now, if you have a 10 by 10 determinant, the first term in your expression is going to be e to the 10th, and then the next term will be a coefficient times e to the 9th, then a coefficient times e to the 8th, and so on. So a very nasty equation with 10 roots that you can get answers for. Mathematical software, when you diagonalize this matrix, it might be an approximate solution, but it can be accurate to many decimal places, will give you all the answers. And as we had in the case for butadiene, you can also get what the wave functions are. Okay, so here's a reminder of the Hückel approximation. We're going to assume that what we call the overlap integral is 0, so they don't matter. All of the interaction terms are going to be 0 unless the term has the two subscripts the same, and then it's just the energy of the atomic orbital. So this is what we call alpha. If I and j are different and they touch each other, then we say we have a beta interaction. So we've already gone through some simpler cases for this, so I think all of you should be able to do this molecule here. So if we do this molecule here, this is a real molecule, benzene ring in the center, couple of four-membered rings on the outside with double bonds there. But every one of these carbon atoms has a p orbital like this, and so we can get lots and lots and lots of conjugation like this. Chemical engineers might well run into molecules like anthracene with lots of rings attached and a lot of aromaticity and so on. So this would be an example of that. So the way we set up the determinant, atom 1 touches 2 and 6, so beta goes in column 2 and column 6. Atom 2 touches 1, 3, and 7, so we have betas in 1, 3, and 7. Atom 7 touches 2 and 8. Well, let me do 3 first, that's easier. 3 touches 2, 4, and 8. So here's 3, 2, 4, and 8. And then look at the rest of this and convince yourself that you can write this determinant. For mathematical purposes, as I said, we can set beta equal to 1 and alpha equal to 0. And so that means if we get an answer 6.3, it's going to mean it's 6.3 beta units higher in energy than the atomic orbital, or different in energy from that. So here's our substitution in of betas and 1s that we have. All right, let me skip in my notes so I see exactly what you have. Okay, so I have stuff on my PDF that I don't need to show you, but this is like, I think what you have known in your notes. So we get this simplified formula, but it's still the 10th order polynomial, and so solving it isn't trivial. For myself and my postdoctoral fellow, I've just recently ordered some mathematical software called Mathematica. I don't know if any of you have used that, but I'm going to have to overcome the learning curve to see how to use that, but hopefully you'll be able to solve determinants like this by matrix diagonalization. Okay, so what are the results? So one could go write out all these crazy things, but these are the results that come out. They're in beta units. 0 is the energy of an atomic p orbital. Our lowest orbital, it's given the symbol B1U here, which is a symmetry symbol, and it looks like this. Mathematically, here is the representation of that lowest orbital, and you can see it has all plus signs. But notice also the coefficients aren't all identical, because atom 1 is not identical to atom 2. But 2, 3, I guess these are 5 and 6, or yeah, 5 and 6, they're all equivalent, so they're all going to have the same coefficient. 7, 8, 9, and 10, 7, 8, 9, and 10 out here, all have the same coefficient, and then 1 and 3 will have the same coefficient. But the key thing I want you to be picking up is notice we have all plus signs matching to each other. If I told you to draw the most bonding orbital for this molecule, it would be this one. We could draw a nice super donut above this ring with a plus sign, and a nice negative wave function super donut under this. All right, so that's just one of many orbitals. This orbital here, it's not quite the most anti-bonding orbital. I don't think I drew that one. This is what's called the A2U orbital, but you can see this would be very anti-bonding. It's plus, minus, whoops. It's plus, minus, minus, plus, I guess. Minus, plus, plus, minus. So, oh, sorry, okay. This is energy 0. So this is the AU orbital right here. So it should come out to be 0 energy because, as you can see, it has 4 bonding interactions and 4 anti-bonding interactions. So hopefully that makes sense now that I got less confused myself. I was going to try to match my first AU up to this one, but this is basically then a non-bonding orbital that does not change the energy of the atomic orbital. All right, the next orbital that is very anti-bonding, it's the A2U orbital here. You see this is plus, minus, plus, minus, plus, minus, plus, minus. So we have a total of 1, 2, 3, 4, 8 anti-bonding interactions, and that brings us up to this orbital right here. And then the last one I showed you was this one. This is a totally bonding orbital. So all of this can be worked out by the Hückel theory. If you have more complicated molecules, then you may need to use mathematical software to get the answers. But this turns out to be quite valuable. This system is going to have 10 electrons. And so you'd have 2 electrons here, 2 there, 2 there, 2 there. And then you are left with 2 additional electrons to put into these 2 orbitals. Since they're degenerate and of the same energy, you would put 1 electron into these orbitals here. So if we believe this diagram, that would mean this molecule is paramagnetic with 2 unpaired electrons. Why I say if you believe that is it's probably not true. The Hückel method is an approximation. We're assuming all of the beta interactions are equal magnitude. And if you took the real magnitudes of the interactions, these 2 orbitals would probably split apart a little bit, and one of them would wind up lower with 2 electrons in it and would not be paramagnetic. Okay, anyway, I hope this gives you a pretty good idea of some of that stuff. Before we leave bonding, I want to do one last example. And I don't have any chat questions, so I can do this. It turns out that 2 of the most prevalent species in space that I'd like to tell you about are H3 and H3+, the ion. And for many, many years, people knew H3 was up there, but they didn't know the structure of the molecule. But now, finally, people have made it here down on Earth for brief periods of time. They made the ions, and so we know for sure what the structure looks like. So what I want to do on this page is basically apply the same methodology as we just used for the Hückel method to decide whether the molecule should be linear or whether it should be a triangular molecule. So the mathematics again looks the same. This is the secular determinant that we had essentially for H2 plus, except I've now expanded it to having 3 beginning orbitals. We're going to take a 1s orbital on each of the hydrogen atoms and see how we can smush them together. And we wind up with these integrals. Here's our assumptions. Again, we're going to say alpha is the energy of the atomic orbital we start from. Here will be the 1s orbital, and beta will be the interaction for an adjacent atom. If the atoms don't touch, the interaction is 0. Okay, so let's do the linear one. Atom 1 touches 2, but doesn't touch 3. 2 touches both of them. 3 touches only 2. So 1 touches 2, but not 3. 2 touches 1 and 3. 3 touches only 2. You can multiply this out. This is the result that you can get. Here I did it with alphas and betas. You get the energies are alpha, and alpha plus or minus the square root of 2 beta. So we can jump down here. This is what our energy diagram would look like, and here's what our orbitals would look like. So the lowest energy orbital would be adding all of the 1s orbitals together. So we push these into a nice blob of 1s atomic orbitals, and we'd have to put 2 electrons in there. We wind up with a non-bonded orbital also, and its nature is we'd have a plus sign way on the left and a minus sign way on the right, but since they don't touch each other, there's no interaction, and so this is non-bonded. But our third electron would go here. And our antibonding orbital, as hopefully all of you would now predict, is plus minus plus, so that would be the least stable. So according to this, H3 linear could be made, and its stabilization would be 2 electrons times the square root of 2 times beta, and then no contribution from this one at alpha. So you get 2.83 beta units stabilization. Okay, we've got just enough time to finish bonding today, Hückel treatment. If we now look at the triangular form of H3, this is the result we would have. Atom 1 touches 2 and 3, 2 touches 1 and 3, 3 touches 1 and 2. You can multiply this all out, and you can solve, and you find out that you get 2 degenerate orbitals, which are antibonding, and 1 which is bonded. Let's see what the chat question is. There's a question, are there practice problems for this section? Yes, and I think they're in their notes. You may have them mingled with some symmetry. Some of the bonding questions I have involve symmetry, so ignore those, but there are some, thanks, Hannah tells us it's page 201. Ignore the symmetry parts. You don't need to figure out if something's AG or B1U or something like that. Okay, well, let's look at the result that we got for the cyclic form. You can see that there's one orbital much lower in energy than the atomic orbitals, and it looks like this. And I think you can all surmise why this should be very stabilizing and bonding. All the 1s orbitals smush into each other in a nice triangular form. We do get 2 antibonding orbitals. We don't use all 3 of the atomic orbitals to generate them, but we put plus wave function next to minus, either this way or the one on the right. And you can see these would be destabilizing, and they're destabilizing by beta units. I made a mistake here. There should be a minus beta up here, and there should be a minus 2 to the 1/2 beta there. So beta being negative, those become destabilizing. Okay, so how much stability would the bonding get from H3 as compared to atomic hydrogen. Each of these two electrons would gain 2 beta, and then the third electron would lose beta. We'd wind up with 3 beta units. So it doesn't look like a big difference, but the simple calculation says the molecule should be triangular like this. And indeed, spectroscopic studies, especially of the molecule in space, show that it is a triangular model. Okay, in the 12 seconds I have left, tell me how we make H3 more stable. I'm disappointed if I don't get any answers. Okay, make it a cation. Very good. That's the answer. That's what I was telling you, that H3 plus in space is even more common than H3. So when you have molecules in space, they could be miles apart from each other and then never collide with anything. So even though they would be unstable on Earth, they can still exist in space. And that's why H3 plus can be so common. If it runs into another H3 plus molecule, it can quickly become a couple of H2s and some H atoms and so on. Okay, well, hopefully this exercise shows you how the Huckel treatment can be useful for even looking at things like H3. It's certainly useful for looking at conjugated systems, and with the computers that we have nowadays, we can put in beta values that are different for different carbon-carbon pi bonding systems, get much more accurate results and so on. Okay, Wednesday we will start on molecular spectroscopy. So hope you all do well, and let us know if you have questions on the grading. Somebody asked if there's a curve factored into the exam. No, the curve wasn't prior to the grades. In general, what I shoot for is to have about 1/3 A's, 1/3 B's, and 1/3 C's in the course. I hope to not have any, or at least not many, D's and F's. I figure all of you have made it this far to get to junior, senior level, so presumably there shouldn't be any really students doing badly in this course. So if you look at it, I think on this exam, somewhere between 35 to 40% of the grades I'm approximating as A's. But other things will come into play. Your class attendance will come into play. If we have any pop quizzes, they will come into play. So this is just a preliminary approximation. Okay, take care, everybody.